Alright, so this is a video to show you the solution of the new generator um, assignment. So let's go ahead and take a look at the requirements first. We're going to have to parse the input. ARGV1 is the number of trials per experiment, so this is how many choices we have to begin with. And then ARGV2 is the number of choices for the first trial. Oh, okay, so I got it reversed. Sorry. So the first one is the number of trials, how many steps we are taking basically, and then the second one is the total number of choices for the first trial. The choices are represented by lowercase English letters in the alphabet. So that means lowercase a is the first one, and lowercase b is the second one, and so on. And the number of choices can range from 1 to 26. The number of trials has to be less than or equal to the number of choices, and then the output should be organized in lines and so on, and remove all the debugging messages. Okay, so I got GDB online GDB here, so that we can just kind of use this as a programming interface. So there's a trick to this homework assignment. Let me remove the unnecessary comments first. So get rid of that. We're already using the C programming language, and now we can get started. So the trick that we're going to use is in the English alphabet. With ASCII code, there is a total order. So the total order is going to help us in this case, because if we organize everything so that, because we're looking at combinations, the U generator only cares about combinations. So in a combination, things, the ordering of things is not actually important, but we are going to exploit the fact that the letters are totally ordered. And as I code it, you will see what I mean by that. So we'll replace this with we have to supply argc and argv. So we say argc and const char star star argv. So this way we can count the number of arguments and also access those arguments. So we want argc to be greater than or equal to 3, because the first one, or argv0, is the path to the command itself, which is useless to us. So now we extract those two numbers. We'll use an unsigned integer, or two unsigned integers, in the main scope of the function main, to remember the number of. The first one is the number of trials, so I would call it number of trials, and the second one is the total number of choices for the first trial. So we say num choices. Alright, so now that we got these two out of the way, we can make an assumption that everything is formatted correctly. There are a few ways to do it. ATOI is one way to do it. So we can now say num trials is ATOI. So technically speaking, if I use ATOI, I should have used int here, but since I'm always applied with non-negative integers, unsignable works just as well. So this would be argv1, okay, and then num choices, it's going to be ATOI argv2. All right. I keep forgetting that in online GDB, the editor is smart. It auto closes things that I open, so I don't have to do it myself. All right, so that should be it. And now we can go ahead and basically call the recursive subroutine. So now we got a few things that we need to think about. One is how do we represent a set, and the other one is how do we get to the end of the recursion and be able to print the set. And because characters are totally ordered, we can actually exploit that to simplify what we need to do. So now the decision is, do I want to just use parameters that are of scalar types, integers and pointers and so on, or do I want to make a structure, so that I can contain everything within a structure? So this way, the flexibility is, if I need to pass one more thing to the subroutine or in the recursive call, I just have to change the structure itself. I do not need to. Um, I do not need to change the function prototype. Um, you know, all over the place. Now C is a compiled language, so changing the prototype is not a big issue because if I forget to change one of the invocations of the subroutine, it's going to be caught by the compiler, but nonetheless it is still a hassle. So I'm going to use the approach of using a structure to store all the params. So I'll just call the structure params, and there are a few things we need to pass along. And I'm not a fan of using global variables. So even though we can use global variables for some of these, I would rather not to. So the first one is how many trials are remaining. Okay, so I'm going to say trials remaining. Okay, now if you want to say num trials remaining, that's fine too. But I think trials remaining is pretty clear that we are just counting the number. And let's see, what do we need? Now, choices is a different thing. We still need to pass that, so we're going to have to say unsigned num choices. Okay. And then we need a string. Okay, so this is the tricky part. Is I'm going to maintain a global string. So we say, well, not global, but we're going to maintain a string to store all the choices along the way of all the different trials. So we'll have to call this string, and we'll say this is our outcome. And this is not an array by itself. It is really just a pointer because it always points to the very beginning. And we don't want to have, we don't want to pass params. How should I say? Okay, we want to pass params by value, but at the same time, we do not want this string to be replicated all the time because only one is really needed. So we have one single pointer to this, which is at the very beginning of that string, and we need to find out, which trial we are actually in. So instead of having trials remaining, there are a few ways to do this. I'm just trying to figure out which way is the best way. So let's change this to num trials, okay? And then we have another unsigned to say, which trial is this, okay? So we'll say this trial, which is also an integer. Are we trial 0? Are we trial 1? And so on. And that's going to come in very handy when combined with outcome, as we will see later. Now, once I have a structure like this, I really don't need to maintain these two as individual local variables. So I'm going to have struct params. I'm just thinking of names to call this. We'll just call it P here, okay? So now P dot trial is, num trials is now a member of P, and so is num choices. So P is what I'm going to pass, but I need one more thing, which is the outcome. Where am I going to store the outcome? That is also a local variable of main because I don't need this to be a global variable. I would avoid the use of global variables whenever it's possible. So I'm going to have char outcome string, and it is going to, I can hard code this to 26, which is the maximum number of trials. Okay, so we'll put a semicolon here, and then define the constant. Now, depending on whether you're kind of old school, brought up in old school C programming, or whether you are using C++ a lot and you like to use the new standard, you can either use pound define, which is the old school way. Has its disadvantages. Okay, so it's definitely not always good, but at the same time, it gets the job done. It also has a lot of flexibilities too compared to using consts. So it's up to you. I personally, it's just kind of old school and, old habits die hard, right? So I'm going to use a pound define here. All right, so now we are ready to do the recursive call. So we'll call the recursive call, just, how about just a function u, okay, or just u, okay? So we call the function u with p as a parameter, and we're going to pass it by value intentionally. So now we need to define that function. For the time being, I don't think it needs to return anything. So we'll have a void function. And the only thing as a parameter is a struct params that is passed by value. Okay. It's not very often that you will pass a structure by value, but in this case, it just makes things a whole lot easier to deal with. And it's not really a gigantic structure to begin with. I know it has got a 64-bit integer here, 64-bit integer here. This one is going to count. This is a 64-bit address, and this is another 64-bit integer. But since we're only doing the recursion like up to 26 times, it's not a big deal. All right. So now the question is, what do we do in function u? So function u, is this is basically our lowercase I. It indicates. Nope, I take that back. Okay, so I is basically num trials minus this trial. Okay, and the first thing we need to do whenever we deal with recursion is to think about how do we stop the recursion, right? So the recursion stops when we have no trials left, okay, which means this trial is matching num trials. So we catch that case first. So we say if p dot num trials trials equals to p dot this trial, oops, this trial, then we can stop. Okay, and I'm gonna say here, we can say no more recursion. Okay, so now the question is, what are we gonna do? I mean, we are there are no trials left. What are we gonna do? So the answer is actually quite interesting because that means we already have the entire outcome done and stored in the string outcome. And the only one thing that we might want to double check is to make sure that it is null terminated. Now the null terminator can stay in place. In other words, I could have put the, oh, that reminds me, I have to use +1 down here, num trials +1, because I need one more byte to store the null terminator, because otherwise it's going to basically we'll have an index out of range kind of issue, except C doesn't really catch it. So it will just go ahead and overwrite a byte that does not belong to outcome string. It's not going to crash this program. Okay, I'm going to tell you, even though we have a potential issue, it's not going to crash this program. And that has to do with when the compiler allocates for a local variable like this, it's still going to try to allocate using 8-byte boundaries to optimize memory access. So with 26, it is 6 bytes away from the next multiple of 8, which is 32. So we actually get 6 additional bytes, in when we say we want only 26. And as a result, the program does not crash because it does overwrite a byte that does not technically belong to outcome string, but at the same time that byte along with 5 more after that do not belong to anyone else. So we are not overwriting something um, that belongs to another variable. So that's the danger of writing programs in C and C++. It just fails silently, and a lot of times, the low-level details can mask the problem until later on, until it does matter, right? Because if we have up to 32 choices, then it would matter because in that case, that one extra byte to store the null terminator is actually going to overwrite the next thing on the stack, which can be a variety of things. So anyway, I just fixed that problem. So I could have initialized down here, okay, because as soon as I know the number of trials, I could just put a null terminator over there. Let me show you what I mean by that. So at this point, I can say outcome string open bracket p dot num, oops, num trials, nope, trials is a null terminator. When you specify the null terminator, you can use 0. You can also use backslash 0 in a single quote. That works too. I personally just use a 0 because we're looking at the ASCII code. There's no need to use the longer format to specify the null terminator. This is already the ASCII code of the null terminator. So this basically automatically terminates the entire string at the very end, which means I don't need to do it here. Now, if you don't do it over here on line 30, then you're going to have to do it over here. Except when you do it over here, depending on what is in params, okay, so you can, if you do it over here, then you basically specify as p dot outcome and then square bracket p dot this trial equals to 0. So you can do it over here too. Obviously, if you do it at both places, it's not going to hurt. It's just very redundant. And then the next thing we do is a single put s, okay, put string, and put string just needs to know where's the beginning of the string that we're supposed to print, and that's just outcome. So p dot outcome it is, and that's it. Okay, so we are assuming all of the other all the recursive calls that led us here has initialized outcome or put values into outcome, and it's ready to go. So now the big question is, what about else? Okay, what about the case when p num trials is greater than p dot this trial? Okay, so when that is the case, we potentially have something to do, right? So what do? Is we need to basically scan through all of the letters that are chosen already, and then we have to find, okay, can we find something that has not been chosen by a previous trial? If so, I'm going to use that, except that we have to do this in a loop, because for each level of trial, it has to basically go through all the elements that have not been used by previous trials. So this is going to be a loop, and in C, not in C++, but in C, variables that you use in the loop, has to be declared outside of the loop. So we have to declare unsigned I first. At least this is the old way of how the C programming language was specified. We can always try the let's just stick with this. Okay, so we'll go ahead and stick with this approach. Okay, and then we say I equals to 0. And we got the number of choices is stored in P, so we say as long as I is less than P dot num choices plus I. So what this loop is doing is it's considering everything that we can possibly use. Now, can we use this? Can we use I or I plus the ASCII code of A as our choice? Well, that depends, right? That depends on whether it has been used before or not. So now we need another loop to go through the outcome string up to this position to see if that particular I has been used or not. If not, then we can go ahead and use it, and if it has been used already, then we cannot use it. Okay. So that means we will need there are several ways to do it. Okay, there's no need to declare another variable, another Boolean, just to store whether we have found it or not. but we do need at least another indexing variable. I know most people use I and then j and then k, but in this case, let's use something other than j. The reason is I and j look similar, and each one does not quite describe what it is. So we will. Okay, so I'm gonna call this previous trial. Okay, and it's just an unsigned and then we have another for loop here. So this other for loop is gonna say previous trial is initialized to 0, and to stay in the loop, okay, we have to either confirm that the previous trial has already used the choice, or it has not, and then we have to increment the number of trials. So the first thing is, and then we have to use a short-circuited Boolean evaluation in this case. In other words, the first thing we want to know is, is previous trial already at the current trial, okay, the current trial, which is this trial. So we have to compare those two. So we have to say, as long as this trial, okay, is greater than previous trial, okay. So that's our first condition to check. If that is true, that means we are indeed looking at previous trial as the index of a previous trial. And then what we can do is to do a compare. Okay, basically we are now asking what was the choice of that previous trial, and does it match I? Okay, so now we got two things to compare. I'm going to put the comparison in its own round parentheses. So the first one that we want to compare is has to do with I, because I is representing a potential element that I can use for this trial. But I want to compare basically outcome p dot p dot outcome and then previous trial. Okay. This is what I really want to compare, but I know this comparison is always going to fail. There's no way it's going to equal, because I is an integer ranging from 0 to 25, and p dot outcome in square bracket is going to be a letter. It's going to be the ASCII code of a lowercase letter, going from lowercase a potentially up to lowercase z. So we cannot directly compare these two because they're off by the ASCII code of lowercase a. So we can just do this, right? We can just subtract the ASCII code of lowercase a, and that's it. Okay, so I'm gonna break this up into multiple lines, just because I can't really quite easily fit everything onto the same line. So it's good to kind of break it up. All right, there we go. And then the close paren goes on to yet another line, and I'm going to close the indentation over here. So if both of these conditions match, which means we are indeed looking at a previous trial, and whatever we chose for that trial does not match what I'm about to use, then we can go ahead and move on to the next iteration. So now we specify the post operation of a for loop, which is nothing more than just, okay, let's find the next trial, okay, and try to see if what I plan to use is going to match that. So we have plus plus prev trial over here. And then the funny thing is, I don't have anything else to do in this for loop. The condition and also the post operation has done everything that I need to do. So when we get out of the loop, we got a decision to make. Okay, when we get out of the loop, we have to basically determine whether I is a valid choice for this particular trial or not. Okay, and you can see that I do not have any additional Boolean variable, or variable used in a Boolean sense, of whether that is the case or not.
So there's a way to make this loop a little bit longer, so that everything is kind of more spelled out. But I'm not going to do that, okay? Because we have all the information already. So to understand how this is going to work, we have to look into how we are exiting the loop, okay? And I just realized I made a mistake here because I want to stay in the loop when I is not equal to p, not equal to the other one, because I want to make sure that a previous trial has not used the one choice that I'm considering right now. So it has to be a not equal to. All right. So when we get out here, we can see that there are two ways to exit this loop. The first way to exit the loop is to fail the first condition, which means, oh, guess what? We have considered all the previous trials and we are exiting the loop this way. But that also means that this condition is always successful. It has never failed. If this condition has never failed, that means all the previous trials um, are have been using elements that is other than what I'm trying to use, which is I, which is from 0 to 25. So that is our ticket. Okay, we basically say if we fail the first condition, so that means if p dot this trial is less than or equal to prev trial, then we have found our own element for this trial. Okay. Um, yeah, so I know the lot. So you might want to think about this logic a little bit. Okay. We haven't really run the code yet, so whether it really works or not, whether I made a stupid mistake. Remember, I used equal instead of not equal to. Yeah, so we're gonna have to see. Okay, but if it does work, then you can try to understand this code. Okay, so let's just say that in here I'm gonna say I is a valid choice for this trial. Then what we're going to do is to put it into the outcome set, except we don't have a set. We basically are abusing the fact that we're dealing with a totally ordered set, and we always consider from low to high. Okay, so now we're gonna say p dot what was it again? Outcome. Okay, which is the string, and then the index is going to p dot this trial, because this trial is a number that ranges from 0 to 25, indicating where we are at this point. And this is just going to be initialized to I plus quote a quote, because quote a quote gives us the ASCII code of lowercase a, and I is really just the integer version of what choice we are considering for this trial. So now that we have chosen what we want, now it is time to do the recursive call. Now when we do the recursive call, we need to this is where it's not really efficient. Okay, I understand this is not very efficient, so we are gonna make another params, and let's not call it p, okay, because we need to clone p into this one. So we'll call next p, okay, and we'll say next p equals to p. So this basically copies all the members of p into next p because they're of the same structure type. So we can just do this to copy everything. It's basically the same thing as cloning in C++, in object-oriented programming. Except one thing has to change, right? P dot next p dot this trial is going to have to increment, because that's really for the next recursive call. So we're going to have to increment this trial for the other one, and nothing else needs to change. Okay, number of trials doesn't have to change, number of choices does not need to change, and the outcome string does not need to change, because the outcome is not really quote unquote a string. It's not, well, okay, it's not an array. It is a pointer. It's a pointer pointing all the way to the beginning of all the outcomes stored in an array. So that does not need to be changed, And let me just double check everything in params. There are 4 of them. Only one needs to change. The rest can stay the same. So now we are ready for the recursive call, which is u, and then we call it with next p as a parameter. And I think this is it. Okay, in other words, there's no else case for this. There's no else for the if starting on line 33. This is because if this trial is greater than pref trial, that means we exited the loop by failing the second condition. But failing the second condition means I equals to p.outcome square bracket pref trial minus the ASCII code of A. But that basically means, some previous trial has used this choice I already. That means I cannot use it. If I cannot use it, I'm just gonna exit. There's nothing for me to do. And so we're going to go for another iteration and go like, okay, give me another potential value for this trial. Okay, that's what it's going to do, which is correct. Okay. All right. So I think we are done. Okay. So it's time to give it a spin. Okay. So let's click debug. Okay. And of course, I forgot to put in the pound include for ATOI. So let me just look up, where I can find that. I'm just on the side. I'm using man ATOI in the Linux command prompt. So it's a standard library. Okay. Yeah, we talked about this in class. Yeah, I do remember that we talked about this in class. But most of the time, I cannot remember what I have said in class. Okay. And the good thing is, it's all recorded. But I think it's faster for me just to, do a man page search to find the correct header file. So let's give it another try. Debug, and we're missing a semicolon on line 57. Okay, let's see. Let's see if it goes to that line automatically. It does. Wow, smart. I mean, I see the underline and I thought, hey, this is probably a link, and it is. Okay, so putting the semicolon here and debug again. Cool. So this time it works. And the first test case is the one that we have talked about in class, which is also the one in the assignment itself. So we want to pass 2 and 3 as parameters into this. So we just say you run and then 2, 3 as our parameters. Press the enter key, and we have a segmentation fault. We ran out of stack space. In other words, the way I checked whether it's time to stop the recursion didn't work. Now, how do I know that, right? Some of you are just asking, but that technically, oh wait, maybe that is not the case. Okay, receive segmentation fault, and the address of the segmentation fault looks actually pretty okay. And the other thing is we can look at the callback. Basically, this is what we see when we use backtrace, right? So backtrace, on the command line of GDB, which is BT, will give us exactly the same thing. It will tell us, where we are, and in terms of the call relationship between the functions. So we're in the first, call of U, and it is failing this one because pref trial is most likely. Okay. I forgot to do one more check. Okay, because pref trial keeps going up, which also means this trial is greater than pref trial should eventually fail. So since this is not working, we can also see the local variables. Pref trial is a 0. Oh, you know what? I think I forgot to initialize outcome. Okay, so we can check it. Let's check the parameter that we are given, which is p, and I'll bet you that outcome is not initialized. So we say print p, and we can see outcome is not initialized. Yep, that will do it. Okay, so with a debugger, I don't need to use any additional printf. I can just examine the parameter, the local variables, and also the callback, to find out what the problem is. I don't need to um, use a whole bunch of printfs, just to find out, what happened here. All right, so over here, I need to initialize one more thing. Okay, so we are initializing. Oh, this is not good either. No, this one is okay. Now we say p dot outcome is outcome string. There we go. Okay, so now we have initialized three things in p, and there's one more, right? Because there's also the current trial, this trial, so we have to initialize p dot this trial and make it a 0. All right, so I think we're good now. And this is also why object-oriented programming is cool, because I suppose you can make it so that even in object-oriented programming, it's not going to save you. The reason why I said object-oriented programming is cool in this case is because you can have a constructor that has 4 parameters in this case, and you have to specify all 4 parameters in order for the function, the constructor function, to be called correctly. So that forces you to actually check everything and before you call the constructor function. But if some people are a little bit on the lazy side and say, well, certain things are always going to be initialized to 0, such as this trial, then it is still possible to forget to initialize this trial um, in a constructor definition. So I guess there's no stopping from careless people like myself, from messing up a program in a careless way. So anyway, I think we are good here. Let's go back to debug again. And then we run again with 2 and 3 as our parameters. And it works this time correctly. So I just want to show you. It says AB, AC, and then it is not good anymore because it says BA, BC, CA, and so on. So that's because now it's printing all the permutations, because you can see how AB and BA, they really should not be both on the output because we are looking for combinations, not permutations. So how are we going to fix this, right? What kind of coding do we use to fix this particular problem? Well, the thing is, we just have to be careful what we are choosing, okay? Because if the choice that I am choosing is not greater than all of the previous choices, then I should not be using it because I'm relying on the fact that everything. Remember what I said? Everything is it's totally ordered. The elements that I can use in a particular trial, all of those choices are they're totally ordered. So I'm gonna make use of that fact. The only question is, where do I insert that code? Basically, I need what I have chosen to be greater than all of the other choices. Oh, I know exactly where to put it. Okay, see in the inner loop here, we are looking for not equal to. So not equal to can be seen as less than or greater than. Okay. So when we get out of the loop, okay, so if I is less than or equal to, then we can just go, because if it's less than, then we should not be using it. So we basically change the not equal to, which is the same as less than or greater than. We change it to greater than. So I has to be greater than in order to stay in the loop. If I is less than, that implies that I'm looking at something that I should not consider. Even if it's not equal to, we should not be using it because the output needs to be sorted. Okay, because that's one way to guarantee that we do not have duplicate outcomes. Okay, so if you're having um, questions about how this works, okay, you might want to kind of spend some time to think about this fix here. Changing the not equal to just greater than, I think is gonna fix the problem, because this guarantees that a new choice is always going to be greater than something that had been chosen already, which basically makes it impossible. If AB is already there, BA cannot be there because A is uh, not greater than B. Okay, so A cannot be considered as a choice, which means that run will simply be aborted because we cannot find anything. BC will still be okay, but BA is not. All right, so let's go debug again. And run 2 3. Oops, I just gave it a number because I forgot about the space between the 2 and 3. Actually, I swapped the space with the 2. That's why it looks doesn't it's not right. So now this time it is correct because we got AB, AC, and BC only. And let me look at this. Yep, AB, AC, and BC. So that's how I would do this. Okay, obviously I used a few tricks to do this. There's no actual set representation, and I also totally exploited the fact that the choices that I can use in any trial, that particular set is totally ordered. So I exploited the fact that it's totally ordered, and basically say if um, an outcome set is sorted, like all of these down here, A, B, A, C, and B, C. That pretty much guarantees that I don't have to worry about permutations like BA, CA, and CB in this case, because those are automatically eliminated. And then combined with saying that when it equals to, it would also exit this loop. Then I make sure that the same choice cannot be used again. Um, so that's kind of how I do this. So for those of you who are curious about so what about when we have 26 and 26, right? That looks terrible. Okay, and in reality this is not terrible at all, because in reality this is all it's going to print. It's just A to Z, but the program will take a long time to run because it doesn't really understand that out of all the permutations, they're all just not going to work. So it's basically going through, it's basically failing out of this loop here, using the second condition all the time. Okay, so this will take a long time to complete, which is okay. It's just, I mean, the output is correct. It's just, taking a long time to do it. So if I do a Control C right now, you can see that um, there's a lot of recursion because it has to go all the way, just to find out that something is not working. And we can always just print p dot outcome just to see what it looks like at this point, and we can see that it has exhausted everything down to the fourth letter. So we still have A, B, E, F left. So that means we have gone through only a fraction of of all the iterations. It's gonna go by at least almost 26 squared. So if you consider how much time it had taken already, that's only about 1 over 26 squared of how much time it would take for the whole thing to complete. So yes, it's going to take a long time, but the thing is, it's not going to run out of memory because I'm not storing anything. So all of these are very transient. Okay. And then the other one is to another extreme case we can test is run 126. So we only got one trial, but there are 26 choices. So this will just print A to Z on single lines, just like exactly like that. Okay, let me show you what the output looks like. So that's just a to Z, each one letter on the line. So these are, some of the test cases here. You can also run 3-4. Okay, 3-4 is not going to be very fun. Okay, it's going to be quite boring because there are only four possible combinations in this case. So we got ABC, ABD, AED, ACD, and then BCD. Those are the only choices. In other words, we are choosing who is missing. Okay, of the four possible choices, because we have to choose three of them, so the only choice left is who is missing. And you can see that there are only four ways to choose who is missing when we have four things to choose from and we only want to have three of them. All right, so that's it. Okay, I'm gonna upload this and share the video on Discord so that you guys can have a I mean, if you want to keep this, that's fine. That's just one way to do it. All right, let me stop the recording and have it uploaded.